If you like the content of this video, please do press the like button and subscribe. The concepts of the second order ODE can be easily extended to higher order ODE, which is of the form. If the coefficients are constant, as before, we set the solution y as e to the power of lambda x. We now generalize the expression of the Wronskian that we studied earlier. The Wronskian can then be expressed in terms of the lambdas, and the determinant is referred to as the van der Waals or Cauchy determinant. If the determinant is non-zero, then all the n roots are different. As before, the roots can be repeated, and complex roots must occur in conjugate pairs. To determine the particular solution, we apply the method of undetermined coefficients, with a modification. If a term in the choice 4yp is a solution of the homogeneous equation, then multiply this term by x to the power k, where k is the smallest positive integer, and satisfies the condition that this term multiplied by x to the power k is not a solution. We can also find the particular solution by the method of variation of parameters that we studied earlier. Higher order linear ODEs with constant coefficients can be solved by algebraic methods, as their solutions are often elementary functions, which are known from calculus. For ODEs with variable coefficients, the situation is complicated, and their solutions are non-elementary. The power series method can be used to solve higher order ODEs. If P, Q, and R have Taylor series representations, that is, they are analytic, then every solution of the ODE can be represented by a power series in powers of x minus x0, with a positive radius of convergence, r. We list below the operations on power series and the identity theorem. Here are some well-known classical ordinary differential equations. We now apply the power series technique to the Legendre equation. Compute the derivatives. Substitute. And establish the recurrence relation. From the recurrence relation, we compute the coefficients. Then we find the solution y. Notice that the solutions y1 and y2 are independent. The table summarizes y1 and y2 corresponding to the different values of k. Note that either y1 or y2 reduce to a polynomial. This polynomial is called the Legendre polynomial. The reduction of the power series to polynomials is a great advantage because then we have solutions for all x without any convergence restrictions. Several important second-order ODEs have coefficients that are not analytic, yet these ODEs can be solved through an extension of the power series method that is credited to Frobenius. This ODE has at least one solution of the form, as shown here. Multiply the ODE by x squared and expand the functions b and c in Taylor series. Compute the derivatives of u. Substitute. And establish the quadratic equation. Depending on the roots, we can find the solutions, as shown here. We apply Frobenius technique to Bessel's equation. Establish the relations between the coefficients. Establish the value of r and a1. Establish the recurrence relation. For nu as an integer, we establish the Bessel functions. When nu is a real number, we choose a 0, in terms of the gamma function, to determine the Bessel functions. The general solution can then be determined, in terms of the Bessel functions.